you should see process management accessible now. And so you have the topics and learning outcomes listed. We want you to read chapters 3 through 5 of the textbook. And we need you to engage chapters 3 through 5 in the slides, right? And you'll notice here that one of the assignments is to download and unpack sysinternals. So that's a pretty interesting thing. You'll see that it's not posted yet, but you'll see that listed under here. And you can get started with the Module 2 study guide and the chapter slides. Any questions before we get started? So in our third chapter, as we talk about processes and the operating system, the 3 easy pieces, the 3 easy pieces being, can anyone remember the first of the 3 easy pieces? According to our Passy Dussault and 3 easy pieces, the alternate textbook. The 3 primary functions of an operating system. Oh, you got to know this for the assessment for Module 1. So can anyone give me one of the 3 pieces? The 3 primary functions of an operating system. I am not picking up on any responses. No one has unmuted their microphone. So I need each of you to unmute.
To store memory. Sorry, I didn't mean to interrupt.
No, that's okay. Persistence is one of those. Yes, there needs to be some main function of an operating system to store the contents of memory, which include data and the instructions to operate upon that data, right, into a permanent store. So persistence is one of the 3 primary functions of an operating system, and that would center on which of the most important structures in an operating system. Which operating system structure would be the manner in which most operating systems manifest the ability to store, to input and output to data files? And that's a hint, that statement I just said. File system. So your file system would be a primary resource that empowers, that would be a primary structure that allows for persistence, right? Input, output. So think files, to and from disks, permanent, non-volatile memory. Okay, the other 2 primary functions of an operating system.
Visualization.
Say again?
Visualization.
Visualization is close. It's a V word, and it means that you are working with a visual representation of an actual physical device. What's the other V word? You're not dealing with the actual physical, you're dealing, say again?
Virtual.
Virtual, yes, virtualization. Thank you. Thank you very much, Sinoa. So virtualization is the primary, I don't want to say primary because each of those 3 main functions of an operating system are critical, but it is virtualization that keys in most to chapter 3 and processes. So as you implement virtual representations of digital components, hardware components, right? What are we talking about? You go into here, and if you're looking at where it says this computer or my computer, if you right click and go to manage and enter the computer management MMC, right? You see in device manager a listing of computers or system devices, right? Digital components. And as the operating starts up, operating system starts up, it loads into active memory, virtual representations of this. And in many cases, these things are on standby waiting for input and output. They're waiting for events or prompts, or they're waiting for a trigger, right? An interrupt. So those are the things that concern virtualization, and processes in chapter 3 is one of the ways that virtualization initiates or implements, right? It is one of the means by which virtualization manifests. You have to have these components in here in order to, they need to be ready to go. The thing that I'm doing right now on the screen would not be possible if processes were not engaged at this time with virtual representations of these devices, okay? And the last, can anyone recall the last of the 3 primary functions? And once again, this is on your module 1 assessment.
Concurrency.
Concurrency is correct. Thank you. Was that, that was Tomi or Luke?
Oh, it's Shinoa.
Oh, it was Shinoa. Okay, I'm sorry. Yeah, my audio on this business laptop isn't always there. Thank you, Shinoa. It is concurrency. So when you talk about the ability to juggle and multitask, that has to do with control mechanisms, right? Our focus on this module, right? As you look at our module, we're going to be highly focused on process management and the main components of process management. Now, when you get into concurrency, you have to synchronize the processes, right? So it just makes sense if you're multitasking and you're juggling simultaneous actions, the ability to concurrently multitask in an operating system can only be possible if you synchronize between these processes. So I hope this kind of bird's eye view or a high level view of the 3 easy pieces, we're going to keep coming back to that and then kind of hammering down. I want you to remember that in chapter 2, it talked about structures, and in particular, there are operating system structures that are related to each of those 3 functions. And you are expected to kind of understand which ones and how they are important, right? Okay, so that said, I'm going to go ahead and begin our review of our processes. So what is the concept of a process? How do you schedule a process so that it's running? What are the operations that you can perform on a process by the operating system? Inter-process communication, that's kind of huge. So as you have all of these different processes that are running, they have to interrelate or interoperate with each other, right? So this idea of interoperation or inter-process communication, IPC, is examples, right? So IPC is an acronym for inter-process communication, or IPC. There are specific ways that processes interact with each other. And we're going to take a deep dive to review communications in client-server systems. So you do see a lot of this processor intercommunication, in particular with client-server models, right? You should be familiar with the idea of client-server already if you're in web applications development, CSC 310, and in some of the other upper-level CSC classes. So I want you to be able to articulate the notion of a process, what it is, and how it forms the foundation for all computation, right? If you did not have a program executing, you just wouldn't have any kind of logical features and functionality. We would stop right there. You're also going to be tasked with being able to describe the various features of a process and the IPC we were talking about, and to explicitly articulate how client-server systems communicate. Okay. So there are different terms that you will engage on different computer systems when we talk about processing. Oftentimes there's a run and terminate kind of notion about a process, right? So a trigger, a script, an event, a scheduled task, something kicks off that job. And in particular, when we talk about data, SQL tasks are often referred to as jobs, right? The idea of a batch, something that is performed in batches means that it fires up, it runs, and then it gracefully just closes out, right? And this is one of the earliest concepts of a process. So what are we saying? We are familiar with a plethora of multitasking capabilities, and I want to encourage you to think exclusively apart from multitasking and how many things are running in the system tray, because that again has to do more with the concurrency aspect of it, right? What is important to understand about the timeshare aspect is that each process as it executes needs to have some kind of limitation or criteria or specification about how it executes, when it terminates, under what conditions does it fire off different system calls or functions. And a lot of this has to do with the internals of a process so that it plays nice with others. The reality is that a process concept needs to include components for concurrency or task sharing, time sharing, right? Because there has to be something built in or cooked in or intended as a process design criteria, right? That allows it the capacity to share the system. If you cannot include that component as you're executing a process, right? There are other safeties or specifications that need to come into play. Sometimes you get really old software where it has to emulate an 8-bit or a 16-bit or a 32-bit, execution environment. And those hail back to the 30, 40 years ago. When you see in the textbook the term job or process, those are interchangeable terms. So you see here sequential, right? So a process execution is laid out in a sequence, and by design, processes are intended to execute in a sequence. Now, it is possible for child processes to spawn, right? So we're going to talk about, or fork, and we're going to talk about that later. But in its most basic implementation, you have this sequence of tasks or statements that execute. The source code is often referred to as the text section. We talk about it in computer science terms as source code, but the program code itself is called the text section of a process, right? So that's important because there are times when you're troubleshooting or operating a process and you want to be able to reference some of this stuff. So a program counter, often referred to as a PC, right, is not the same as a personal computer. Hello? A program counter, we've heard about this in our first module. A program counter, often abbreviated PC, does not refer to a personal computer. Okay? The process registers are embedded and integrated with program counter functionality. So this is one way that an operating system keeps tabs on a running process through the program counter. Any questions at this point? Some of this should be review terms from your, from your CSC 242. Hopefully you remember some of this. So a stack memory contains temporary data, right? So when you have a function that needs to execute, the stack data embeds the function parameters, the return addresses, and the local variables. If I say which component of memory for a process stores local variables, hello, you're going to say, oh, that's the stack, right? Any questions?
Not at this time.
Okay, so global variables, you may have heard the term before, global variables. These are storage objects that can contain data or instructions or components, parameters, and criteria of. If they are globally available between processes, those are stored in a data section, the part of the process called the data section. So if you have a piece of information, if you have a datum, singular, or data, multiples, right, that need to be universally accessible, especially in the context of inter-process communication, you know, those would be considered generically as data. The heap contains memory dynamically allocated during runtime. So as you're firing off processes, there are occasions where you have a journaled operating system that needs to audit the execution and health of a process. There is memory that is dynamically required while a process is running, especially when a process crashes. But any memory that is dynamically allocated as a process is utilizing resources would be found in the heap and in the part of the process component known as the heap memory, right? So local variables, stack, dynamic memory, heap, global variables, data section. Any questions? All right. So in terms of process concepts, until it is recalled from the file system stored on disk in non-volatile memory, right? It's passive when it's stored on the disk. It's considered active when it's read into memory. So even if it isn't like executing in particular, if it's loaded into memory and it's not stored on disk, it's considered active. A process is considered active when it is part of system memory, and I don't mean disk memory, okay? Program becomes a process when the executable file is loaded into memory, right? At which time we call that an active process. When an executable file is loaded into memory, it is now active. Now, that's not the same as a running service, but we'll cover that distinction a little later on. Any question about this distinction here? Okay, so how do you initiate a program? Well, you can utilize a GUI, you can use a command line entry manually, so you can intentionally load a process, or it could be something that's loaded when the operating system boots automatically, right? Or it could be something that's scheduled with a timer, right? We would call that a cron job, C-R-O-N in Linux or Unix. In the wonderful world of Windows, we would call that a scheduled task scheduler, right? One program can be comprised of several processes, and it often is, okay? It's usually true that a lot of applications and programs are not just one thing, but they're several. And remember from our first module that there can be dependencies between those processes, right? There can be instances of the same process that are running that in a multi-user operating system are executing at the same time, right? Okay, so here's the data section that includes global variables. Which is it that includes local variables? Hello, hello. Local variables. Oh, we just went over it. Stack. So local variables, global variables, dynamic data. You see it stack and heap have a nasty habit of taking up more memory. What do we find in the text section of memory for a process? What's another term for that? Hello, hello. Okay. I need everybody to unmute your mics and just tell me you're still with us, please.
Yeah, I'm still here.
I'm here.
Okay, that's two.
I'm here as well.
Okay, that's three. Need to hear from a fourth. Luke, are you here,
Yeah, I
Luke?
answered, yeah, I answered already.
Okay. Did someone answer, but the mic was muted? What do we find in text? In process memory in the text section? Like the code itself?
The code. Oh,
Oh
Yeah.
yeah, the source code.
Yeah. Well, the code itself for the executable is in the text section. And I hope that I'm not refreshing your memory about something, you know, source code is compiled and then it becomes machine code. Everybody knows what I'm talking about, right?
Yeah.
So code can generically mean any and all of the above, right? So you have in the case of interpreted programming languages, that source code is interpreted and then it becomes active as machine code, right? So in any case, I did say source code earlier. I just want you to think in terms of code generically, all right? Everybody knows that you have to like compile or interpret source code in order to get a program to do anything, yes?
yeah.
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 Okay, all right. And in terms of something that's actively running, at the point that it's actively running, you know, the code you're dealing with down here is, you know, that's the operational side or the business end of that code dynamic. So you have machine code executing. All right, process state, right? So one of the tasks of an operating system as it manages processes is to monitor the state of a process. So as it's executing, it changes its state. If it's being created, that's a new process. So as it's loading into memory, that's a new process. That's its state, is that it's new. If it's executing instructions, that means it's running. If it's waiting for some event to occur, it's waiting. If the process is waiting to be assigned to a processor, that means it's ready. And if it's terminated, that means it's over and done with. Now, what's the distinction between these two states right here? Let's look at this a little closer. But I'm a little frustrated because this ought to be like right here. So if I'm going to change this again. There we go. New, ready, waiting, running, terminated. I'm going to edit this video so that what we've related here is consistent between this slide and this diagram. Okay. My apologies for any confusion. Any questions? So I was,
No.
yeah, I was on a roll and then we got to the diagram. So the previous slide was not really consistent with this. So ready and running shows waiting on the sideline. So now what is it that is also, all right, so let's talk through this a little further. When you have a process that's running, depending on the priority or privilege of the process, right? As soon as it receives the CPU resources, the processor resources, it may execute immediately. So you notice these arrows account for almost like every condition here. Now, it is not always the case that a process executes as soon as it's started. I would say on most multitasking operating systems, it's really more like you have a new process that's ready and it's waiting and watching for the right conditions, because most multitasking operating systems are juggling so much. So you're going to find differences in this. You're going to find differences. And one of the things that we talk about when we get to persistence and the file system is this idea of priority. So you have different privilege and priority levels for specific programs. And for those that are preemptive in nature, those that in our first module, does everybody remember we talked about ring 0 and the deepest, most privileged, most sensitive, highest priority processes concern direct access with the hardware? Does everybody remember that?
Yeah.
Okay.
Yeah.
Okay. So you do have priority levels, and you do have differing degrees of privileges for process execution. And so yeah, this diagram is useful because it shows you each of the different contexts. But I would argue that there are plenty of cases where it has the processor resources and then it's waiting and watching, especially for multi-user systems. All right, that's all I'm going to say now. So a PCB, the process control block, this is one of the means by which an operating system manages processors. And here you see the reference to the program counter, right? So in the PCB, you'll see information on what state the process is in, where it's listed with respect to the program counter, and then there are cross references to CPU registers and memory management information and IO stuff. So PCB is actually a very important, it's a very important method of controlling a process and managing processes. So if we ask, what's the clearinghouse, or where do you find all of this stuff in one convenient place? The answer would be the process control block. So you need quick information on all these things for a process. Where do you find them? The process control block. Any questions about the PCB?
No questions.
Okay, we're gonna handle this last slide and then take a short break. So this is quick information about a CPU switching between processes, right? So you can kind of get a feel for the sequence of how things flow. You'll hear quite a bit about interrupts and how interrupts help or perform the necessary controls. Interrupts provide necessary controls in order to switch or multitask, right? So what are we saying? This is one of the internals of process structure that allow for a process to play nice with others. And if this stuff is not, if the operating system process is not intentionally designed with this in mind, you have ill-behaved process. Can you think of anyone on the planet that would take this knowledge and intentionally make something unstable? Let me repeat the question. Can you think of a scenario where someone would intentionally take this knowledge and understanding and use it to design a process that scrambles the egg and makes things unstable?
Hackers.
Hackers, yes, hackers. If they understand the internals of an operating system and the universal methods and agreement for how to manage processes, they can yoke this knowledge to create all sorts of mischief, right? So it's also useful for you to know this for troubleshooting. So just as we do in networking and as we do in hexadecimal and as we do in computer architecture, in operating systems, the first resource that is provisioned uses the 0 number, right? So the first process of an operating system that it fires off is referred to P sub 0. Everybody, repite usted, por favor. P sub 0. Which kind of reminds me of Mortal Kombat. Sub-Zero. Anyway, P sub 1. So when we use, that's how you pronounce that, process P sub 1, process P sub 0. So this is the second process. You notice the PCB, right? So there are corresponding PCBs for each process, and those are used in the management of each of these as they are idle and execute and idle and execute, right? Any questions? This is an excellent diagram in terms of just laying out how this makes sense. Threads, okay. So you've heard the term thread. We're going to be dealing with multi-threaded stuff quite a bit in later modules and chapters. But in terms of basic information, every process has at least a single thread of execution, a primary thread. You cannot have a process without having the one primary thread. Now, obviously, you can have processes that behave unto themselves, or you can have processes that are intended to intercommunicate with other processes by design. So you have this exclusive versus interactive view, exclusive versus interactive view of things. And why am I bringing that up? This is something that we mentioned in module 1. We said that there are different flavors of process, right? And some are intended to kind of live into a world on their own, and they don't know of, they're not aware of anything else or anyone else outside of their own little realm. And then you have process that are intentionally designed for shared memory and communication between processes, right? Does that ring a bell from module 1? We talked about OS structures, kind of, sort of, maybe.
No.
Okay. So when you have interactive processes and you have shared memory, the implication is that you have more than one primary thread in the process. What are we saying? If you have a process that's intended to be exclusive, you may have more than one thread, but they're not going to be architected. They're not going to be designed to tag in with other threads from other processes, right? Generically speaking, the more exclusive a process is, the fewer threads it would have. And I know I'm overgeneralizing, but one thing to understand is that you can't have a running process if you don't have at least one single thread of execution, a primary thread, okay? And you have those details in the PCB. And it says, okay, see the next chapter. So this chapter is about processes, and what's the next chapter 4 about? Threads. Okay, so as a method of execution when it's running, we're going to do a deep dive. That's what chapter 4 is all about. Just remember that you have to have at least a single primary thread in order for any process to execute. And quite often you have multi-threaded processes, especially when the intent is for inter-process communication and shared memory models. That it kind of puts everything on steroids. And we're going to spend a whole lot of time on that in chapter 4. Process representation in Linux. I kind of wanted to look for process representation in Windows. Yeah, okay. Guess not here. I've seen that somewhere else. Oh, there it is. Creating a separate process in the Windows API. So here's a telltale. Did everybody see this?
Yeah.
Okay. So your first clue is that we're in C or C++, well, C, because we have headers. So we have to include header files, right? So this is the source code for process creation in the Windows environment. So if you see windows.h, we're looking at a Windows process. Let's zip back to this. In Linux, processes are viewed conceptually in a different manner. You'll notice here the reference to PID. Does everybody see this?
Yes.
So what are we saying? Not only does a process have at least one primary thread, but a process is also assigned a process identifier or a PID. And as you're executing source code in C, these are the things that are defined, kind of like defining a variable in a programming language, right? And then you're storing these in what common resource, the clearinghouse of all this information. Where would, when this thing executes to initiate a process, the stuff you're seeing here, where would this information go? Just want to make sure you're picking up on what we've covered so far. Put another way, where would you look to find this information once these statements execute?
Can you repeat? I'm not quite understanding the question.
Okay, so when a process is initiated, this is the representation of a process that executes in Linux. So let's pretend that these programming statements are executing in order to initiate a process, to create a new process, right? Where is the information that results from these executions stored? Where would you find all that information conveniently? Which can be referred to as kind of like the clearinghouse of process information. The PCB? You remember the PCB? Everybody? PCB?
Yeah.
Okay, so this kind of information, right? Just remember that the PCB is this clearinghouse for information as a new process is loaded and as it's running, right? That information. And the components of the PCB, you'll see a correlation between the statements here and the graphic we just showed in the PCB. Okay? Didn't the,
Oh, I understand now. Okay.
yeah, didn't it say something about the state of the process, right?
Yeah.
Yeah, yeah. And then you have memory management structures, right? Heap, stack, all that. Right? Okay. That's the point we're trying to make. So, yeah, it's not always apparent, but there is a correlation between what you're seeing here in Linux. And there are analogous components in the world of Windows, right? So I'm going to zip ahead again to the Windows because our author is so into Linux. So we're creating a child process. There should be a reference in here to like allocate memory. So there's a memory component. Where's the PID? Process information. Okay. Yeah, we'll parse that out a little. Oh, there's information about the thread, right? Primary thread. We'll deal with parent and child in a bit, okay? Yeah, so this is some of the criteria that you're going to see loaded into the PCB as well. Size of the thing, memory components, and so on. All right. Any questions before we get into scheduling? So what's a PC again? What is a PC again?
Personal computer.
Oh, that's a good one. I'm so glad we had this moment. And I'm sorry, I hope I'm not being too annoying. I know I'm kind of going 2 steps forward and 1 step back and 2 steps forward and 1 step back. There's quite a few weeds in this process chapter. And I kind of want to forge ahead and then jump back just to make sure that we're tying it all together. The PC is what's the C stand for? All right, let's change the question. What is it? What component of processes in an operating system do you think handles the process scheduling? The process controller? Didn't we say process? Please tell me I'm not. Process control block.
Yeah.
Process controller.
You mentioned it.
Oh, program counter. Program counter. Program counter. Process controller. No, all right. So I'm mixing up terms. Program counter, right? Processor registers. So PC stands for program counter, not process controller. But the control of processes includes process scheduling. And the program counter is a component that allows for scheduling to occur. What am I saying? You have to be able to keep track. You have to track the different statements and the sequence of execution, right? And especially if you're multitasking. So the program counter its activity is complementary to program process scheduling. Okay, I hope I haven't completely confused people. And generically, you could say, okay, this is all a part of process control, program counter. All right, maximize CPU use, quickly switch processes onto the CPU for time sharing, right? So whenever you hear the term timeshare, multitasking, that kind of thing, that's scheduling. Once again, if a processor is not intentionally architected or designed to include these components, it tends to be very ill-behaved and doesn't run in any stable kind of fashion. It doesn't play nice with others. Does that make sense? Now, these are
Yeah.
important. Yeah, now these are important terms. So the process scheduler is something that works hand in glove with the program counter. Okay, the program counter. Process scheduler works hand in glove with the program counter. And it maintains scheduling queues. Okay, so generically, when you have all the processes in the system listed, we call that generically the job queue or process queue. Remember, the term process and job are interchangeable, right? So if you see process queue or job queue, it means the same thing. That's a listing, that's a set of all the processes that are in the system, right? And the ready queue. Now, remember this business, the ready queue? You remember I said there is a distinction between ready and waiting? And it's a subtle one, but it's an important one.
Yeah.
Ready and waiting? Yeah? Okay. I would like to know whether or not the ready queue, would we call that a waiting queue if it was waiting? Or generically, is ready and waiting the two categories of processes that are actually in the ready queue? Well, it depends on the design of the operating system. I don't want to appear like I'm kind of dodging bullets here, but everyone realizes that firmware and operating systems are a huge landscape for technology, right? And as we have the Internet of Things, these smart devices that are connected to the internet, these smart devices that have firmware, the internal design of the operating systems, it could be that some OS internals, especially when we come to firmware, aren't as robust, and they kind of take shortcuts and lump everything together. And one of the things that I would like to ask you is whether or not, this is just food for thought, for more mature and more industrial strength operating systems, think supercomputing, would the intentional architecture of a queue that differs for ready processes versus waiting processes be an advantage? Would that conceptual distinction be important for a certain CPU or processor? And the short answer is, oh yeah, it all depends on what processors you're using and how you're going to tune the operating system, right? So generically speaking, you could have an operating system that has a ready queue and a waiting queue, depending on the function or primary purpose of that operating system. I'm just extrapolating that this is a generalization here, and it's an example. Device queues, okay? So whenever you see device queues, you're looking at processes that are waiting for access to a hardware device. And processes migrate among the various queues. So it's generically listed among all of them. Oh, it's in the, which comes first, ready or waiting, according to the diagram?
According to the diagram, it was ready first.
It was ready. It was ready first. And waiting was, okay, so you got the CPU, now you have access to the CPU, but you're waiting on an event to execute, or you're executing. It's one of those two states, right? So yeah, you could have a waiting queue. Could have a whole series of processes that are just waiting and watching. And can you imagine that that would be an important resource when it comes to device queues? You might have a device that's tied up. It's completely saturated with one process. Can anyone think of an important IO device that would be completely locked into or devoted to a singular process? Let's just say a hacker wants to use that idea to devote all of the resources on a system to maximize the output of a device. Has anyone ever heard of a denial of service attack? Distributed denial of service attack? What you're doing is commandeering the network interface so that you can flood output data, just random, just a flood of just data, fire hose data, right? Output, and you're sending it to a target, and there's 10,000 other devices that are doing the same, right? It's just food for thought. Just want to provide some context here. Any questions about queues? So queues are critically important to the function of a process scheduler, which again works hand in glove with the, what is it called? What's the PC? Hello, hello?
Program counter.
Program counter. Do not let me trick you on the module 2 assessment, where I have an assessment item that says, what does PC stand for? And it's program controller or process controller, right? I'm going to mix it up. So you can count on it. Ready queue and various IO device queues. Okay, so here you have some graphical representations of this kind of stuff, right? So this is cute, magnetic tape. That used to be part of mainframe computers. And actually up until 20 years ago, you could get a tape cartridge that you could put into a tape drive that was connected through a parallel cable to your PC to back up your disk data. True story. Yeah, you'd have like a cassette or an 8-track cartridge, except connected to a PC through the parallel port. The printer port, meaning there was parallel data transfer instead of serial data transfer. Everybody knows what I'm talking about, right? Yes. Okay, here's what we're going to do at this point. We have 2 minutes and it's 1/4 after. So I'm going to keep going so we can get through these last few slides and then we'll stop. So process scheduling, you have all these different queues. So conceptually, the author is it's provided this diagram. So yeah, here you see the ready queue, direct access to what? The processor, right? So that's conceptually, this diagram is consistent with what we saw in the previous slide. So when a program is ready, that means its next interest is to lay hold of CPU resources. And if you're waiting, you're down here. If you're executing, you're here. If you're executing and there's any kind of data going input, output, you're also involved with an IO queue. Okay? Does this make sense? Has anyone ever heard of a timeout?
Yeah.
So you could have a hardware device that's too busy and it's commandeered by another process. So it's good to have this this built in to the way your queue operates. So in case you run into a brick wall, it's like, you're not ready yet, you're not ready yet. Well, so if a time slice expires, I would say that another thing that happens is that depending on how the process is designed, it might loop around and attempt to access that hardware device again, or it might go into a waiting mode. Yeah. Short-term schedulers, long-term schedulers. So short-term schedulers tend to be designed to, well, they're centered on the processor itself. And the long-term scheduler is centered on jobs, as in triggered by events or triggered by a schedule, an intentional schedule. So input output to file, temporary caches written to disk memory and so on. You're going to see some of that stuff going on here. So here you see that processes can be described as either CPU bound, meaning it's living in this realm, or IO bound, meaning it's living in this realm. Whenever you have more IO in the mix, you tend to be dealing more with a long-term scheduler. So, and here you see this last statement. Everybody sees this, right? Long-term scheduler strives for good process mix. So if it is designed and centered to support multitasking. If you have a balanced mix of processes that behave well with each other, a robust and dependable long-term scheduler is in the mix. Whenever you're dealing with burst mode, you're dealing with a lot of CPU activity, that's a short-term scheduler. And I don't know if you know this, but if you've ever seen a PC in burst mode, like in a gaming context where there's a lot of video being processed or something, or you see in a data center where there is a huge demand on like storage area networks for data across the network, right? Where the disk store is provisioned across a high bandwidth network. Those burst scenarios tend to suck the life out of other processes. Does that make sense?
Yeah, that makes sense.
Okay. So I think this would be a good place to stop for today. So what we've done is basically examined some of the primary concepts, and there have been a few potholes here and there. Just remember PC is program counter, and it works hand in glove with a process scheduler, right? Don't let me mess up your terms. And once again, I'm going to do some very quick mini editing. Back here when we were talking about this slide right here, these two slides right here. New, ready, waiting, running, and terminated, that seems to be more compatible with this diagram. So conceptually, if you're following down that original slide and then you get to this, it can, there's a disturbance in the force, right? And I'm glad that this diagram followed on the heels of this slide, so that now we have a new order here. All right, so on Thursday, we're going to pick up with slide 17, and that'll be the addition of medium-term scheduling. So what happens if you're not dealing short-term or long-term? What happens if your computing system has a lot more resources and it can juggle more?